Hello everyone, this is part 2 of section 1.4, separation of variables and the applications. And last time we went through many examples of separation of variables, and this was our last page of notes. We saw 4 examples where we found the particular solutions. So now some applications. And to be able to understand the derivations of our formulas, we need to recall the formal definition of the derivative. And if we consider f the function and t the independent variable, then we could say the derivative of f with respect to t is, remember the formal definition, delta t tends towards 0, the limit of that is, of f of t plus delta t minus f of t all over delta t. So we will look at examples involving natural growth and decay. And it turns out that the differential equation, the general differential equation dx dt equaling kx, is often a mathematical model for these situations. Our first example is compound interest. So the formula here is stated, but I want to show how it's derived. If you consider let's say the change in the amount, okay, so A is going to be the amount to be equal to the rate, the percentage, times the amount, times the change in time. So that's the amount, let's say, of interest added. So this is the amount of interest in a short time of delta t. So then if we take that equation, because it's going to be the rate, whatever the percentage is, times the amount in there, times that change in time. If we take that equation and we divide by delta t, we have delta A over delta t equaling R times A. And now we consider the limit as delta t approaches 0 of, well, you could think of both sides of the equation, but on the right, introducing the limit wouldn't matter because there's no t variable. But this delta A over delta t, that actually is this portion of our derivative, which we call the difference quotient, because delta A would be the change in the amount, so that is the amount at the initial time plus that extra short interval minus the amount of the initial time over delta t. And now you can see that it fits the form for the derivative, so that's going to be equal to the RA. And now this all represents, in terms of the form of our derivative, that represents dA dt. So therefore we've derived the formula that dA dt is equal to R times A. Okay, so similar situation for population growth. If we take P to be the population, called beta, that is lowercase beta, the birth rate, and lowercase delta, the death rate. And we consider K to be the difference between the births and the death rates, then that formula is derived by considering the following. The fact that there are going to be beta times the population times the change in T births, and there's going to be delta times the population times the change in T deaths during some short interval of time. And so therefore we can say that the change in the population in that short interval of time is going to be the difference, the births minus the deaths. And then if we factor out a p delta t, we'll do a left-handed factorization, or excuse me, a right factorization, and we'll have beta minus delta times p delta t. And then if we divide both sides by delta t, we get the change in population over the change in time is going to be birth rate minus death rate times the population. And now we consider taking the limit as delta t tends toward 0. And again, just like the last example, we don't need to take the limit on the right hand side because t is not involved. So then that gives us the limit is delta t tends toward 0. The change in population, similar to the change in the amount in the last example, is going to be the population at the new time, t plus delta t, minus the original population, p of t, all over delta t. And that has to equal, okay, at this point, what we can say is k times p, because we had stated that k here is beta minus delta. And so the left-hand side now represents the derivative of the population, the time rate of change of the population, that is, the derivative of the population with respect to time, and that has to equal k times p, and we've derived our formula. Okay, so then we have radioactive decay, and we can think about radioactive decay as basically population growth, but with no births, just constant deaths. So there's going to be no births, and we're going to put n for the amount in place of p. We're going to take k to be greater than 0 and put it in place of delta, and because there's no births, the birth rate is 0. So the formula, let's take it from we consider the dp dt equaling the beta minus delta times p. Okay, we'll replace that k for now by the beta minus delta, but now impose all these conditions where we take n in place of p, beta is 0, and delta is going to be our k. So therefore we'd have that the time rate of change of the amount is equal to negative k times the amount. And there's our formula for that. Okay, so you don't need to worry about the derivations, but certainly nice to see them. And here's our first example. So suppose we discover in an attic an overdue book which our grandfather owed 30 cents 100 years ago. So basically we're given that at t equals 0, that is, we'll consider 100 years ago to be the initial condition, the amount that he owed was 30 cents. And we're also given that the fine grows exponentially at a rate of 5%, compounded continuously. So the rate of 5%, you want to convert that to a decimal 0.05. And we want to know how much we would have to pay if we return the book today. So basically the amount is question mark when t is 100 years. Okay, so we start with our formula for compound interest, and that is that dA dt equals R times A, and we could substitute the rate because that's not changing. Note that the amount's changing, but the rate is not. So we could say dA dt equals 0.05A, and then we could separate the variables. First off, in differential form, we could say dA is 0.05A times dt. Divide both sides by dA. So dA over A is 0.05 dt. That's our familiar when we integrate. So at that point, you could throw the integration symbol in front of each side. That's our familiar natural log. So we'll just say the natural log of A, then it equals 0.05, integrating that constant. We pick up the variable of integration t, and we call this the natural log of c, because remember, good practice is when you have a natural log generated on the left, your constant can be expressed in terms of a natural log. Because then in the next step, when we Eulerize, take e to be the base of both sides of the equation. Okay, let me break out some scrap, because we're going to see this so often that we just want to skip this step in the future. That is that e to the 0.05t plus the natural log of c can be thought of as follows. Just think of we've mentioned this more than a few times already. Think of the common base rule for multiplying bases of e. Multiplying common bases, we add the exponents, so we're going to treat the 0.05t as our a, and the natural log of c as our b. So therefore this would be e to the 0.05t times e to the natural log of c, but then the natural log of c is just c. So what we want to do in the future is just go right from this point to saying that this is equal to c e to the 0.05t. So you don't have to show all this, simplification. You could just jump right to that point. So we get that the amount is ce to the 0.05t. Alright, so now I'll bring it up here for the initial condition to solve for the constant c. We have that at t equals 0, the amount was 30 cents. We'll just get rid of the dollar symbol. So into our general solution, 0.30 equals c, because if t is 0, this would be e to the 0, which is 1. So then we get the equation, general equation, that a equals 0.30 e to the 0.05 t. And so you have to show the derivation of the formula. If you were in a business course, they would just simply give you the formula that the principal, or that the amount is equal to the initial amount times e to the rt. And that's basically what we derived, okay? But you have to show the derivation. You can't just use the formulas. And so what we want, so let's say now t is 100 years. So then the amount is going to be 0.30 e to the 0.05 times 100. Okay, so then you can obviously use a calculator to check my work. I came out with $44.52, rounded to the nearest penny. Okay, so that's a compound interest example. Now something a little bit more interesting. We've got a Chernobyl type situation. Gives us the half-life of radioactive carbon, and there's been a nuclear accident, and has left the region 100 times at the acceptable level of cobalt radiation. And we want to know how long will it be until the region is again habitable. And this is from the textbook. It mentions ignore the possible presence of other radioactive isotopes. Okay, so basically what's given is that the half-life is 5.27 years. So t, will use a subscript of 1/2, is 5.27 years. Alright, which means that the amount, remember we're going to use n for the amount, is equal to half of the original amount. So I'll use n sub 0, or for the original amount, times 0, when the time is 5.27 years. Now this data here, the half-life, is actually going to allow us to solve for the constant k. Basically we're just seeing exponential decay here, as we'll see. So we're given, in terms of the initial conditions, let me state them this way. There's many ways you could do it. Let me say that t sub 0 is 0, and the original amount is 100 times the acceptable amount. See, we have to state that because we don't know what the acceptable amount is. So, but we do know that the original amount is 100 times what is acceptable. And what we want is the time it takes for the amount to reach back down to the acceptable amount, n equaling n sub a. So we start with the differential equation that the time rate of change of the amount is equal to negative k times the amount. And we have to solve. There's nothing we can substitute. We don't know what k is yet. Okay, it's not the 5.27. That's not the value of k. K is determined based on that time. But first we have to separate the variables in general. So let me say dn equals negative kn dt, so differential form. Divide by n. So dn over n is minus k times dt. We'll integrate both sides. You could have jumped in and put the integral symbol in that step, but I took an extra step to show it. We've seen this more than enough and get used to it. You know, dA over A, dP over P, dN over N. That's the natural log. So the natural log of N is equal to integrating K, it's just a constant. With respect to T, we get negative KT. And then we say plus the natural log of C. Because again, there's a situation where we generated a log on the left. Now, again, you don't have to show this in the future. I'm going to show it one last time. You take E to be the base of both sides. But then E wipes out the ln, we just get n. And this becomes, as we've argued more than a few times now, just CE to the negative KT. Okay, so hopefully you're comfortable with that. If not, look back at the argument that we posed more than a few times. Okay, so that's our general equation, but now we need to solve for C. And the initial condition was that at t equals 0, n equals, okay, for the sake of making this a little bit simpler, I'm not going to call it 100 n sub a yet. I'm just going to call it n sub 0, okay, which is the same. But that's going to tell me that upon substitution, I replace n by n sub 0, that's going to be C. Because e to the 0, if t is 0, this is e to the 0, which is 1. So then that gives me the general formula that n is whatever the original amount was, times e to the negative kt. Alright, and at that point, we need to find the value of k. And we use the half-life. And the half-life is t sub 1/2 was 5.27, meaning that n was half of the original amount. So substituting into our formula, now we have half of the original amount, or 1/2 n sub 0 is n sub 0 e to the negative kt. But now we can cancel out the n sub 0s, replace them by 1s if you want to show that, and we get 1/2 is e to the negative kt. And we need to solve, or negative 1/2, I'm sorry, it was at this point here, I made a mistake. When I substituted the 1/2 n sub 0, I should have also substituted in the half-life time. Just 5.27. So then 1/2, canceling the n sub o's again, 1/2 equals negative 5.27 times k. Okay, and then at that point we're going to take the natural log of both sides. We've got to undo the e to get to the ln, so natural log of 1/2 is the natural log of this side. Really don't need to show that because you know that what the natural log does is undoes the e to give us its exponent, negative 5.27k. Okay, so then dividing by negative 5.27, k is the natural log of 1/2 over negative 5.27. And you can go to your calculator and carry this out to 4 decimal places. I don't want to lose much accuracy, so carry it out to 0.1315. And so now that gives us the formula for n in terms of the original amount, n sub 0 e to the negative 0.1315t. So that's the amount at any time. Alright, let's bring it up here to finish it off. Okay, so there's our equation. I'll recopy it up here. N is n sub 0 e to the negative 0.1315t. And what we want is the time when the amount equals the acceptable amount. But also note that the original amount was 100 times the acceptable amount. So therefore, making all of the substitutions, but before I show, let me just substitute the original amount first. So n equals 100 n sub a e to the negative 0.1315t. Okay, now we'll let n equal n sub a. And now we're going to be able to solve for t. First off, the n sub a's cancel. So we get 1 equaling 100 e to the negative 0.1315t. Okay, I'm going to show the steps explicitly here, but I want you to think about trying, how can you get this mentally? Well, first we divide by 100 to isolate the e. Then we would take the natural log to undo the e. And let me just go right to the fact that that's equal to its exponent, because we took the log of both sides. And then we would divide by the coefficient of t. Okay, so in the future, I'm going to be doing all these steps mentally. Okay, we'll see that in the next example. Okay, and then at that point, use your calculator. And t is about 35 years. Okay, so the final application is Newton's law of cooling. And Newton's law of cooling states that the time rate of change of temperature of a body in a medium of constant temperature, call it A. A is for ambient temperature, is proportional to the difference A minus T. So we use uppercase T for temperature, lowercase t for time. So when we say the time rate of change of temperature, the derivative of uppercase t with respect to lowercase t, so it's proportional to the difference A minus t. But as we saw in our mathematical models, proportionality, just some constant multiple. So the time rate of change of the temperature can be equal to K times A minus T. So that's the formula for Newton's law of cooling. And so we have an example, and we're given a cup of coffee, initially 95 degrees, read through it, room temperature is 20, after a minute it cools to 90 degrees, how long to take to reach 65 degrees. So here's the givens and the requireds. At t equaling 0, time t is 0, the temperature T is 95 degrees Celsius. Then we have this intermediate time. Oh, and also A is 20 degrees Celsius. And we use A for ambient temperature. And note that that's going to be a constant because that's the temperature of the room. So after 1 minute, so we have this intermediate condition, the temperature is cooled to 90 degrees Celsius. And then we want to know how long will it take. So T is question mark for the temperature T to reach 65 degrees Celsius. Okay, so we start with the differential equation. Time rate of change of temperature is K times the difference between the ambient and the temperature. The ambient is a constant, so we can substitute it. Note that the temperature uppercase T is always changing. Excuse me. I need to separate the variables. So the differential of uppercase T is K times 20 minus uppercase T times the differential of time. Dividing both sides by 20 minus T. Get the differential of the temperature over 20 minus T is equal to K times the differential dt. Now K is a constant, so the variables are separated. I'm going to rate this as 1 over 20 minus T times the differential of time, or of temperature dt, and the integral of K times dt. Certainly we can integrate the right-hand side easily. But for the integral, I'm going to go off to the side here. You have to be very careful about this one. For the integral of 1 over 20 minus uppercase T with respect to T, you have to actually consider a U substitution. We're going to try to fit the form of du over u by choosing u to be the denominator 20 minus t. The differential du would be minus dt, because the derivative of t is 1, and you'd have to modify by a negative. So negative du would be dt. So that is, this denominators are u, and the numerator represents negative du. And then we get the form, we've got to factor out that negative of du over u, which would be negative natural log of the absolute value of u, or negative natural log absolute value of 20 minus t. Okay, so very important to understand the concept of the u substitution. You could do all this mentally. You don't need to show that to me. You could, do all that work mentally. That's fine. But it's very important to realize that this is going to be negative natural log of. You could use absolute values. You really don't need them because assume the temperature is positive, of course. And that's equal to integrating k with respect to c. We get kt plus, okay, we can call this the natural log of c because there's a natural log of here. There's a natural log over here. But I'm going to call it the natural log of c1. And the reason why is because I have to multiply, in order to get at uppercase t here, I have to isolate the natural log by multiplying everything by -1. So the natural log of 20 minus uppercase t is going to be negative kt. And then here I'm going to say plus the natural log of c. So it's just a different constant. It's really negative natural log of c1, but I replace that by the natural log of c. Okay, now we could Eulerize, and you don't need to show this step again. Making e the base of both sides. This just becomes 20 minus t, and then we have, as we've talked about many times, c e to the negative kt. And let's solve for uppercase t by transposing. I'll move the negative t to the right and the c e to the negative kt to the left. And say that t is equal to it would be 20 minus c e to the negative kt. Okay, so now the initial conditions. At t equaling 0, the temperature was 95. So 95 equals 20 minus c, because t is 0, that's e to the 0. So this would be 75, but then negative, so c is negative 75. So our equation so far is that the temperature is 20 minus a minus 75, so plus 75 e to the negative kt. Alright, and we'll go up here. I think this should give me enough room. The intermediate conditions is what allows us to solve for the coefficient of t in the exponential factor. So this determines the rate of decay. So at t equaling 1, the temperature was 90 degrees. See, if after a minute it was 80 degrees, that's gonna change the value of k to be exponentially decaying at a faster rate. But at T equaling 1, temperature is 90. So 90 equals 20 plus 75 e to the negative k times 1. Okay, now I'm going to do this mentally. So follow this. It's similar to what I talked about in the previous example. To get k, we're going to subtract 20 from 90 to get 70. Then divide by 75 to isolate the e. To undo the e, we'll take the natural log, but then we're going to divide by this negative 1. And that'll give us the value of k. Okay, so if you need to, look back at the steps involved in the last example. And this gives us a value of k of 0.067. So now our equation in general is that the temperature at any time is 20 plus 75 e to the negative 0.067 times t. So what we wanted was how long does it take, or t is question mark, when the temperature is 65. So in our general equation, 65 equals 20 plus 75 e to the negative 0.067 t. Okay, and then I'm going to do it again. First, subtract 20 to get 45. Then divide by 75 to isolate the e. Take the natural log to undo the e. And then that leaves us with the exponent. And now divide by the negative 0.067 to get t. So then obviously you use a calculator, and t comes out to be roughly 7.4 minutes. I did make a mistake when I was looking at my solution. I made my 9 look like a 7. This value of k is actually 0.06, 0.069. Okay, so make sure you make that correction. Not too difficult here though, thank goodness. So negative 0.069 was the value of k. Okay, so that ends section 1.4.